Okay, hello everyone. Welcome to our next session. This is the 5th session of the chapter 5. So let me first of all to share my screen. So today's session we are going to discuss Apache Cassandra architecture, and our guest speaker is Fadai Ganjaliyev. He is assistant professor of Fadai University. And this session is hosted by GOAP. GOAP is open source accelerator. And today's agenda is about, I will go quickly to about through our today's agenda. It's after brief introduction, we will go through the presentation part, and then at the end we will have Q&A session and wrap-up session. So I'll share with you the contacts of our speaker. So as I mentioned before, this is the 5th session of chapter 5. And this session is hosted by me. I'm Elvira Sirajdada. I'm currently doing my MBA at Ch5 and joining from Seoul, from Korea, but originally I'm from Azerbaijan. And if you don't mind, Fadai, we can start the presentation. So just quickly, our code of conduct is this. These seminars are for learning, benefiting, and contributing. This is not marketing and no selling, no competing. And we desire the equality in our community. Thank you for all participants for joining this session. And Fadai, thank you very much for accepting our invitation and for hosting this session. So we can start, if you don't mind, the presentation part right now.
Okay. So let me share this my presentation. Just give me a second.
Yeah.
Okay. Thank you, Elvira Hanım. Thank you, Sakobay, for this great opportunity to have a talk here. So my name is Fadai, and I am an instructor at AD University. I've been teaching primarily database-related courses for the last 6 years there. And in parallel with that, I used to be a database administrator as well. So, today our presentation is going to be about one of the most popular NoSQL database management systems, which is known as Apache Cassandra. So I'll try to keep the talk as compact as possible. And as I go, please feel completely free to stop me and ask some clarifying questions whenever you want. So at the end, we'll have some time, as Elvira said, for Q&A as well. So, but in the middle, you can stop at any point. So, okay, let's go then. So as you see, Apache, so as I said, Apache Cassandra is a NoSQL database management system. So as you see right now on the left, so Apache Cassandra borrows ideas from two systems. The one on the left is Google Bigtable. The one on the right, the Amazon Dynamics DB. Cassandra was designed in Facebook, and back then it was used for the Facebook's inbox search. Now there were very strict requirements for the system that will be serving the inbox search. So this made motivated the engineers to start thinking about some systems that can serve requests of users that are submitting their requests to the inbox search, and that actually gave the birth to the system Cassandra. So at this point, we're not going into details of those techniques under the Google Bigtable on the left and those techniques under the Amazon Dynamics DB on the right, but we'll eventually be touching them later on. So this is how Cassandra was created. So a few points about why we need a system like Cassandra. The first one, as you see, guys, is that Cassandra is very, very fast. So especially for write-intensive applications. So when you have an application that, for example, digests lots of time series data, for example, like sensor data and something similar to this, so Cassandra is a very good choice for this. The other point about Cassandra, which is the second one, you see that it's always on. So it's a highly available system. So we'll be talking about these details later on, but this is, for now, this is just high-level information. The third one is that it is almost linearly scalable. So what that means, if your system needs more power, so what you can do is you can add more and more nodes, and your throughput of the system will be improving linearly to the number of nodes that you add in. And finally, one of the greatest things about Apache Cassandra is that it supports multi-data center deployments. So that means if we can have a cluster in one geographical location, and we have a cluster in another geographical location, and Cassandra is pretty fine with this. So it will allow you to work with both of the clusters, replicate data, maintain availability. So for example, when one of the data centers is not available, the other data center will be brought online and will continue serving the requests. So these are some 4 primary reasons why we may need to consider Apache Cassandra. So on high level, Apache Cassandra looks like this. So it's just a ring of nodes. Each of these brown circles that we see, this can be thought of as a standalone machine. Right? So we may have a physical machine, or we may have a virtual machine, or it can be an instance in the cloud, for example. So each of these circles is an individual node. All of them form a cluster. And the architecture that we employ here is shared nothing architecture. So that means each of those nodes is quite independent. So they don't share anything with each other. So this is not to say that they don't exchange messages. Of course they do, because this is a cluster, there's communication between them, and etc. But each of them can be thought of as an independent actor in the system. So every node can make decisions because every node has information about the whole cluster. Okay. So this is how so now we're zooming into any of the nodes. And what we see is that for any node, we will have an instance of Cassandra running, and part of this data will be in the memory. This is the upper half of this circle that you see, and the lower half is disk or SSD, so disk storage. So some of the data for Apache Cassandra node will be in the memory. The other part of that will be on the disk. So as I said, one of the great things about Cassandra is that it is really very good at digesting data. So if you have a write-intensive application, so the Cassandra is a very good choice to this. And as you see on the screen, those reads and write operations are coming and going from a node, and that node is, as I said before, so it's quite independent, so it can serve user requests freely. It can contact other nodes, can be a coordinator node, can fail itself, other nodes will replace this node, and so on and so on. So there are many scenarios that can be related to this. So a few words about how this cluster works. So first of all, it's important to know that Cassandra cluster is a peer-to-peer cluster. So what that means is that there is it doesn't employ master and slave architecture. The other name for this is leader and follower, primary or standby. So Cassandra doesn't follow this architecture. It's peer-to-peer system. So what that means is that each of these nodes that you guys can see now on the screen, those brown rectangles, which is a node, each of them is independent and everyone is equal. So there's no master node and there's no slave node. Like all the operations go into the masters, and when something happens to the master, so other slaves have to vote so that to elect a new master. So something like this doesn't happen in Apache Cassandra because everyone is equal. So it's a entirely peer-to-peer system, right? So Cassandra also employs replication. So what that means is that if you have, I think I'll have more examples on this. If you have a data come into a node, so you can configure how many replicas for this piece of data you will maintain in your cluster. So for example, put in there 1 into the cluster, and replication factor is configurable. So if my replication factor is 3, I will have 3 copies of this data, 3 replicas of this data in the whole cluster. Right? And also, as I said before, when you have multi-data center deployments in Cassandra, which is fully supported by it, so replication can happen across data centers as well. So, and also replication is totally configurable on a data center level. So on this data center, we may have 3 replicas for a particular piece of data. On the other data center, we may have 2 replicas, for example, for the same piece of data. So the main takeaway from this page, I would say, is that, which is very important and which is very useful, is that Cassandra is completely peer-to-peer system. So there's no master and slave here. So, and another thing to mention here is, for example, we see on the top a read or write request comes along, picks up the node that is on the top as the coordinator node, comes down, and one of the nodes turns out to be failed, right? So one of the nodes is down. So that's not a problem for Cassandra because it has a replica on the other node. So instead, when it finds out that this data is not available, this node is not available, it can freely go to the other node and get the data from there, because we have configured it in such a way that it will hold data replicas, right? So this is a to have a to give the main idea of how multi-data center deployments can work. So in this scenario, what we'll see is we have data centers in different geographical locations, right? So the one on the top is somewhere in Amazon cloud, the one on the right in UK, the one on the bottom is in New York, and the one on the left is in San Francisco. So these are different data centers, right? But logically, it can be still thought of as a single cluster, right? And then, for example, if the data center on the bottom turns out to be down, fails for some reason, right? Other data centers will be there, so they're alive, they can continue serving your requests. And this is not the end of the story about multi-data center deployments, because once the one on the bottom goes down and not available, when it comes back, as we see in the next step, Cassandra will take all measures itself automatically to make everything synchronized. So when the New York cluster in this scenario was offline, right, it was not available, right? And so, of course, users continued to work with the cluster through Amazon, UK, and San Francisco multi-data centers, right? So data was coming, going, and so on and so forth. But the data center that was there in New York, it was lagging behind. It was falling behind because, for example, for the last hour, it was unavailable, right? So in this case, after it comes back, Cassandra will automatically resynchronize everything. So it will detect that the data center in New York has come back, so it needs to synchronize data, the new data that came to the cluster when this New York data center was offline. So when it comes back online, the data from the other data centers will be streamed to that cluster that is there in New York. So everything will be synchronized automatically by the cluster. Okay. So every node in a Cassandra cluster, as I said, every node can be either a physical machine, virtual machine, or it can be an instance in the cloud, right? So there's an interesting thing in Cassandra cluster, and it is very useful to have some idea about this, which is the concept of snitch. So in a Cassandra, because Cassandra cluster is a distributed system, so there is network involved in this. So there can be nodes in the same data center, in the same rack, in the same subnet, and so on and so forth, right? So snitch in Cassandra is a component that allows the coordinator node to find out the information about the network topology. So when a request comes along, right, snitch kicks in and helps the user request to find out whether the piece of data that this user wants resides in the cluster. Gossip is another interesting thing inside of Apache Cassandra cluster. So as I said before, so this cluster is peer-to-peer system, right? So every node is equal and everyone knows about everyone else. So all these nodes that you currently see here from 10 to 80, they have the same power. No one is different from anyone else. And gossip is that protocol that allows these nodes to communicate to each other. So through this protocol, every node will stream information about itself to the other nodes. So for example, one node will stream to the other, to randomly picked up 3 nodes. The other node will pick up another 3 randomly nodes, and then will stream data to them, and so on and so forth. So this is achieved by the gossip protocol. There are lots of internal interested details to this, right? And so these are two important things to know. And snitch and gossip, these are two things that are very tightly related to each other. So I'll repeat, snitch allows user application to find out the network topology in the cluster. Gossip is a protocol. Gossip is a protocol that allows all the nodes to communicate and spread information about the cluster state among themselves. This is an important thing because this is one of the things that helps the system to be peer-to-peer, right? I was wondering if there's anything at this point that guests may be wondering about. Maybe somebody has any questions or.
I think these nodes, can they? Oh, sorry, you had a question?
Continue, I will ask later.
Sounds good. So curious that should it be like VMware, or just because I'm from DevOps perspective asking that, can they be containerized and run in cluster in Kubernetes around yourself? And
yes, completely. So probably open source version of Cassandra may have some limitations in that sense, but there is commercialized version of it, DataStax Enterprise, which commercializes Apache Cassandra. They support all these things that you mentioned, like in Docker, Kubernetes, and things like this. So it is fully supported by them. Yes.
Nice.
Okay.
Okay, I wasn't in the beginning of the call, so I might have missed that part. Is Cassandra in-memory database or just a regular on-disk database?
No, it is not an in-memory system. It is regular on-disk system. However, so if you take any individual node and so an instance, right, any node in this cluster, so portion of the data structures, certain data structures, they will reside in the memory. For example, this thing called mem table. Other structures will be held on the disk. For example, SS table. For things such as mem table, row cache, key cache, Bloom filters, they will be there in the memory, right? But there are other structures that will be on the disk. So by design, Cassandra is not an in-memory database system. So it's a disk-oriented database system. Okay.
Okay, thank you.
Okay, good. Okay, so in this scenario, what we see is how data finds its place in the cluster, right? So on the very top, we see an application is trying to insert key X, right? So it comes down to node number 80. And at this point, there can be a question, why does it pick up exactly 80, not 10 or not 70? There is a separate protocol that dictates how a coordinated node should be picked up for this user request, okay? And let's say for this example, node 80 has been picked up as a coordinated node. Before we go back to this example, I'd like to mention another thing is that in a Cassandra cluster, every node, because it's a peer-to-peer system, every node can act as a coordinated node. Every node acts as a node that stores user data, replicated data, and at the same time, it can act as a coordinated node because everything is peer-to-peer. So when this query, as you see, it comes down to 80, 80 takes this key X, hashes it, and returns token. Now, token is nothing but some sort of an integer, right? So this token simply says on what node this piece of data resides. This hashing happens via the thing called partitioner. So there's a separate component in the Cassandra cluster, partitioner. Partitioner takes that key, hashes, returns token. Token says the exact address where this piece of data resides. And for this example, we see that it says, hey, for X, you have to go to node number 50 because 50 will store your data, right? So this is how a request is routed in a cluster. In this scenario, what we have is we have a modification of the previous one with one thing with the replication factor, right? The one that you see, guys, on the very bottom of the cluster, right? The replication factor is 3. Replication factor is something that everyone is aware of, like dictates how many replicas your piece of how many replicas this particular piece of data will have in the cluster, right? So for this example, replication factor is 3. Now that same X has been inserted, it's been hashed, token returns 43, that the primary replica goes to node number 50, as you see there, and 2 more replicas we need, dictated by the replication factor. So that will go, one of them will go to 60, the other one will go to 70. And as a result, we will have 3 replicas of this specific tuple in our cluster. Should cluster number 50, for example, fail, the other 2 replicas at 70 and 80 will be able to serve, will be able to continue serving user requests. Okay. So this is an example of how this replication factor works in case of multi-data center deployments. So we have 2 data centers, data center 1 on the left and center 2 on the right. And as we see, Cassandra allows us to configure replication factor per data center, right? So in data center 1, we see that replication factor is 3. So we want 3 replicas of our data in data center 1. However, in data center 2, we need only 2 replicas, right? So this illustration is just to show that replication factor can be configured differently for different data centers within one and the same logical Cassandra node, logical Cassandra cluster, sorry. Right, the same scenario happens. So we insert in a key X, it gets hashed, token returns 43, it streams data to 3 nodes in data center 1, and then it will stream to other nodes in data center 2. So in total, we will have 5 replicas for our data for this X, right? 3 of them will be in center 1, 2 of them will be in center 2. So I'd like to give you some information about consistencies, Cassandra, which is an important concept. This is not replication factor. This is something different. Consistency defines how many nodes in a read or write operation we want to respond to our user request to consider the request to be successful. So if, for example, I'm saying consistency level is 2 and I'm inserting data, then what I can do is, so what happens is that Cassandra makes sure that at least 2 nodes respond so that to consider the write successful. Okay, so so in this example, for example, let's go back to this example, the one that you're seeing right now on the screen. If the replication factor is 3, when I'm inserting this X, I can say consistency level will be 2 for this insertion operation. Right? So when we insert in, it will make sure out of 50, 60, or 70 out of this 3, at least 2 respond that insertion was successful. And then it returns to the application a message that your write was successful. It doesn't mean that to the 3rd node, it will not write at all. It will do it, but it will do it asynchronously. But 2 is enough to tell the application that your insert is successful. What consistent level, what replication factor you should have in your application is entirely up to the application requirements. So there's no one-size-fits-all recommendation here, right? So another interesting thing in a Cassandra is known as hinted handoff. Okay, so this is this can rescue you from in a situation where one of the nodes where you have to write data is unavailable when this write occurs. Right? So let's take a look at this example one more time. So we're inserting key X, we hash it, it goes to 43, right? And we say consistency level is 3, for example. That means that this write must occur to nodes number 50, 60, and 70. Now, if, for example, 60 is down, but the consistency level is 3, that means 3 writes must occur, right? So in that case, the coordinator node, which is 80, will hold that data that it couldn't send to 60 because it was down, right? Will hold it with itself, which is called a hint. And then later on, when 60 will come back, it will stream that hint from itself to that node 60, which was down at the moment of write. So this technique is known as hinted handoff. So it holds hints just because the node to which it was supposed to write was unavailable at the time of the write, right? So this is, and then when the node comes back, that node, the data from the coordinated node in the form of hints is streamed to that online node, which was down a few minutes ago.
What if it doesn't come back?
Well, what?
If the node goes down and doesn't come back?
If the node doesn't come back, then the hint will be removed after a certain period of time, which is controlled by a parameter. There's a parameter that indicates for what time period a node can store hints. If, for example, by default, it's I think it's 10 days by default, which is quite configurable. If it doesn't come back, 10 days expire, then hint will be removed.
Okay.
Okay. So another great thing about Cassandra is that it can scale as your needs, as per your needs. You have data size growing. This can be through because typically it is because of the application, right? So this current throughput is not enough. So the application requires more and more throughput because there are, number of users increased from 5 million to 15 million, for example, a number of active sessions, okay? So in that case, what you're doing is all you need to do is just to add a node. Now, I'll say another interesting thing here is that adding a node to a running Cassandra cluster is pretty straightforward. You just need to change one or two files, configuration files, put there some seed nodes, IP addresses, and things like this, and start this node, and this node will join the cluster. Theoretically, it is simple, but there are certain things that we need to take care of, especially in large clusters, because whenever you add in a node, because this node has become a new member of this cluster, it now should own a portion of certain portion of data. So the other nodes will stream data that should be owned by this new node. So some measures has to be taken, but the procedure of addition of a new node when you need more capacity is pretty straightforward. So take a look at this cluster for a second. We have 20, 30, and 40, right? So in this scenario, what we're doing, we're adding two nodes, one between 20 and 30, the other one between 30 and 40, right? And once we do this, they take some sort of new IDs, 24 and 32, I think, right? 24 and 32, right? And once this happens, the other nodes will start streaming data that must be owned by this new node, right? So, for example, just a simple example, let's say we have 3 nodes and each of them holds ranges from 1 to 33, from 34 to 66, and from 67 to 100, right? So when you add the 4th node, now all these 100 values, 100 integers should be uniformly distributed among these 4 nodes, right? So this is why those 3 nodes that now hold data, they will stream a portion of the data that they own to that newly joined node. Okay, so what I'm trying to say is that the procedure, as you need more power, what you can do is you can add more nodes to a Cassandra cluster. When you don't need it anymore, you can take these nodes offline. There are procedures to add it smoothly. If addition turns out to be problematic, then you can do it forcefully. You can assassinate a node. You can shut down a node and bring it out of the take it out of the cluster. So certain tricks are there available. Okay, but in huge clusters where you know that terabytes of data will start streaming just because you have added new nodes, certain measures have to be taken. Okay, and as I said, I'm always trying to keep my talks very short and compact, even though we have allocated an hour, I think, for this. I think we'll finish much earlier. So here what you see is, just let me, yeah, this is the write path. So the way we do reads and writes in Cassandra, we call, so those write procedure and read procedure in Cassandra is called respectively write path and read path. So here, guys, I don't suggest we go into more technical details, but rather we discuss some high level how it looks, right? So this rectangle, this circle that you see, this is a single node. Inside of this node, as I said before, as a follow-up to one of the answers to an answer to one of the questions, so portion of the data resides in the memory. We see here memtable A, memtable B, right? A portion of the data resides on the disk, which is commit log, SS table for A and SS table for B, right? Here's an interesting thing. Every table in Cassandra cluster will have an associated structure known as memtable. That memtable is an in-memory data structure. Okay, so that's held entirely in the memory for all the time, constantly. The associated on-disk representation of that memtable is SS table. So for example, you see here memtable A in the memory, and on the disk you see SS table A, right? So one on the same table, so you have a create table command, for example, that creates a table for your Cassandra cluster. That table will be stored in the memory in the form of memtable, and on the disk in the form of SS table. These SS table structures are immutable. That means once they have been created, they cannot be changed. And these SS tables, they get originated from memtable. So one memtable gets full, for example, or a table gets truncated, this memtable gets flushed on the disk, and SS table gets created. Then, of course, for one and the same table, you may have many SS tables. Then later on, compaction process will kick in and will merge and will coalesce them. So compaction can be thought of as a different presentations, maybe. And also another structure that I like to tell you a few words about is commit log. Commit log is there for recovery purposes. Whenever a write occurs, two things happen for this write to be successful. First, that write must go into the memtable, and second, it must go to the commit log. So once these two things successfully complete, then Cassandra will tell the client that your write has successfully completed. Okay, so in this example, we see an insert statement. This write comes to the node inserts it into memtable, and memtable gets flushed and becomes an SS table. And at the same time, this write must go to the commit log. So memtable and commit log must be written for the write to acknowledge the application about successful completion, right? SS table gets created later on. So memtable will eventually get flushed, and it will create a new SS table. And as I said, as these SS tables accumulate over time on disk, compaction will coalesce them.
Is SS table same as just a regular database table, or?
No. SS table internally, SS table is a column-wide store, also known as a white column store, sorry, not column-wide, so a white column store. Internally, it's a key value pair. It's just a hash table. It's not in the form of relational database management system where inside of a page, you can see column attribute values for individual rows. Internally, SS table is nothing but a key and value pair. Okay.
Okay. Also, do we use SQL as query language here, or it's just an example you wrote there?
No. It is Cassandra's CQL language, okay, which very much resembles SQL. All right. Commands are very similar. All right. So insert, update, delete, create table, drop table, truncate table, and things like this. They are very similar. However, there are certain things in Cassandra which are not there in a typical relational database system. For example, joins. Cassandra doesn't have joins. Cassandra doesn't have foreign keys. Cassandra doesn't have other things, transaction-related things, like commit and roll back. It doesn't have this, right? Because Cassandra says you inserted data, it's gone, right? So it's done, inserted, done. You cannot roll it back. You can roll it back on the application level, but the database doesn't give you any opportunities of this kind. Later versions, recent versions of Cassandra come with lightweight transaction concept, which allows you to do this. But as to the feedback, in practice, lots of people are not using it. Okay, but this CQL language provided by the Apache Cassandra, it very much resembles SQL, but certain things are not supported.
So in relational databases, we use transactions to make atomicity happen, right?
Okay.
How does it happen in Cassandra?
In Cassandra, you don't have the concept of transaction as such. In write of a single write on a row level is entirely atomic. So either the whole write will complete, like you insert in a tuple, right? Either the whole write will complete, or it will guarantee that if portion of this write fails, then the whole write will not occur. However, if you want to do something like you have 5 writes in a batch, like to think of a like transaction, it doesn't have this. It doesn't have this concept. It drops these asset guarantees. Okay, so it simply says like, hey, when you insert in data, I will insert it on a tuple level. I'll make it atomic, but for example, 5 tuples, I can't guarantee atomicity. It could be that 3 of them will go fine, 2 of them will fail, and that's fine for Cassandra. Okay.
And if someone, yeah, okay. And if someone wants to read something when I want to write somewhere, how does it happen? Like concurrency, basically.
Concurrency is achieved. So let me tell you this. Concurrency is achieved on the tuple level. If you're, for example, if you are doing a multiple writes, okay. If you're doing multiple writes, the idea here is to follow. So the mechanism that follows here is to guarantee that the latest write wins. Okay, but if you are doing so for the when you're doing a write and at the same time when you're doing a write and at the same time you're a read, this is achieved by the latching. So latching is an in-memory protection of tuples rather than in the form of asset locks. Okay, Cassandra doesn't have the concept of locks. However, it will guarantee that reads and writes, they will not interleave on a tuple level, not on a transactional level, but on a tuple level. This is not to say that it doesn't use anything like a lock, right? Lock is a transactional level concept. It uses latches to achieve this. Other databases call it mutexes, for example.
Okay, clear. Thank you.
Okay, good. Yeah, so this is, guys, how write procedure runs through in a Cassandra cluster. And finally, read path. Read path says, read path shows us how a read operation occurs. Okay, here I'm not showing all the data structures involved in a write process. Okay, so but some main of them are these. So when a read comes along to a Cassandra cluster, these are the data structures that are involved in this read process, such as I'm reading from top to bottom: row cache, mem table, Bloom filter, and key cache. So row cache stores the most frequently used rows, followed by search in the mem table. Then there's a Bloom filter that can tell you, hey, maybe the key that you're looking for is there in this SS table, maybe it's not, right? So if a Bloom filter fails, then key cache can also be checked. There are other data structures that are involved here as well, like partition index, partition summary. They are there in open source version of Cassandra, but partition summary index is not there in DataStax Enterprise, the commercialized version of Apache Cassandra. So because they are in one type of Cassandra, but not in the other type of Cassandra, this is why I eliminated them from here, okay? But the point I'm trying to make here on the read path is just to tell you guys that it doesn't go directly to disk to find the thing that it's looking for. There are some in-memory data structures that are involved in this read path, okay? For example, let's take the row cache and mem table, the first two. If the row that is looking for is there in the row cache, it will return, right? No need to go to the mem table and down this hierarchy, right? If it's not there row cache, it can be there in the mem table, for example, okay, and so on and so forth. So as you see again here, the SS table A, this resides there on the disk. The other 4 data structures, they're held entirely in the memory. And pretty much each of them is configurable, like key cache, sizes of them, key cache, row cache, mem table, Bloom filter, you can configure them. They're totally configurable. And finally, to conclude all this story, so when so so I'm telling the students, my students also, because we started with relational database management systems, and along the way, talking about different database stores as well, data stores as well. So it's important to know that in Cassandra, you're not trying to normalize your data. In relational database management system, one of the let's say best practices is to normalize your data at least to the third normal form. You're doing this in order to avoid data redundancy, avoid data update anomalies and things like this. In Cassandra, you don't sort of care about this, and you shouldn't be, right? Because Cassandra says, hey, you have to denormalize data rather than normalize your data. Yes, Cassandra runs on, Cassandra is very fast, but it will take you more space if you run the same application on a relational database management system, because you're denormalizing your data, and plus to take into account the replication factor by which you have to multiply the space, which will be owned by the database, right? So Cassandra takes a different approach. Like, I don't need normalization, I will denormalize data, but as a trade-off, I will be very fast. And by the way, in Cassandra, the way we model our data is known as query-based modeling. Query-based modeling. So if you're interested, you can take a look at this later. So this means that we need to analyze queries that the applications are running, and based on them, we have to create our tables, rather than apply the third normal form and split our table data around in tables and then join them. Cassandra doesn't support joins. So this is why it wants to denormalize, to pre-join your data in tables before everything. So this will be about me. I didn't want this talk to be long for the first time. So this is all for today. Thank you everyone for coming, and thank you for your questions, and thank you for listening. It was
thank you for that, but we still have a question. I think I just waited a bit long, so if you don't mind.
Sure, yeah, I'm here. Yeah, go ahead and ask.
Awesome. I want to just a bit understand from use case perspective, like when we, let's say, do it, because let's say why I need to pick Cassandra over MongoDB, or Postgres also have in a way, but it's document based, like for example MongoDB, and is it the distribution piece or any other things? Basically. Yeah.
Okay. So one of the reasons, for example, if you compare Apache, Cassandra, and Postgres, let's take these two, and then we can compare with MongoDB, for example. One of the reasons, so reason number one is scalability. Reason number two is availability, for example. So what I mean by, for example, availability, in a Postgres type of database, which is a relational database management system, like you will have master and slave architecture. So let's say you have one master and 5 slaves, right? So when your master fails, probably for some moderate applications, that's not a big deal, but for some critical applications, it's important. Every second in a single minute is hundreds of, it's a lots of money for the company. So in a Postgres type of database, what will happen, the master fails, there will be some time spent for the standby databases, for the slaves to vote and to pick up, to elect a new master. That takes time. That takes time, even just a 5 or 10 seconds, that's a huge time. In a Cassandra, in a Cassandra database, you as a database administrator, let's say, you should not be thinking about things like this. Like if one node fails, for example, what's going to happen to the rest of the nodes? If you properly accurately design your database from scratch, taking into account the application requirements, replication factor, consistency level, and things like this, then you can, 99.99% guarantee that, you will have your system available all the time. So any request will return you something, even though that will not be consistent. They may be eventual, right? So a few milliseconds here or there, not a big deal maybe for some applications, for which Cassandra is just fine, right? So this is number one. I talked about high availability. The other one about scalability, right? So relational database management system also supports sharding, okay? But Cassandra was designed with certain things in mind, like when you add a node, yes, of course, there might be some slowness when a node comes along and you have to wait for some time, but that will be much better in a system like Postgres, which was not designed with this in mind. So this is not to say that Cassandra is a silver bullet, it solves all your problems. It was designed for specific types of applications, and it's very good at that. MongoDB, by the way, regarding the MongoDB, we compare the two. As you know, as you said yourself, MongoDB is a document type of database, right? So it works with documents, right? Your document can be large. MongoDB, by the way, also guarantees that write to a single document will be atomic. But now let's think about it for a second. Like, let's say you have a nested document, right? What's going to be faster, right? To read, change, and update a single document, or to insert just a single tuple, the way that Cassandra works, right? And MongoDB, by the way, also employs master-slave architecture, which is very similar to Postgres, right?
Yes.
Yeah, go ahead.
And the search functionality-wise, how does it make it easier?
Search functionality means?
In database, if you want to query this searching.
Like you're writing queries, you mean? SQL queries?
Yeah, I think you mentioned that we have the write nodes and read nodes and this kind of thing. Yeah, like.
Okay, I got it.
If you just select all, and so the performance piece that would be faster in that case.
See, no, it is not going. The way it's going to be faster is this. In a Cassandra, if you run a query like select from table, okay, no predicates, for example, let's say this query by default will not run. It will tell you you are risking to access all the nodes. The way Cassandra works is, the way Cassandra works is that it will want you a partition key in your query. For example, select from table where country equals Azerbaijan, for example, right? So it requires that predicate there for the partition key, the way Cassandra works. In it, Cassandra, so coming back to your question, what about improvements on the search? For this type of search, Cassandra is super fast. It's just a matter of microseconds. For this type of search, select from table without any filters, that is going to be slow because it will access all the nodes, right? But when you say partition key equals something, it has to go to an individual node and plus few replicas to satisfy your consistency level and return your data, right? So, and if you can override this default behavior. It will tell you select from table, no filters. That's dangerous, just a warning. If you want, okay, so you can add a clause like allow filtering. It will still do this, but it's on your own risk, you know, so. And about the write functionality. So you mentioned about search. I'll tell you a few words about the write is that the commit log in Cassandra. So as I said before, when you're writing to mem table and the commit log. Commit log write must be successful for the write to acknowledge the application that it's okay, because otherwise you can't recover your data. Commit log is for those purposes. Commit log internally is built in the form of LSM, log structured merge tree data structure, which is append-only data structure, and it doesn't support like in-place updates. So to the commit log, you append and only. So this is another reason that write is so fast in Cassandra, like you are right. Mem table and disk. And the disk write itself is changed for those purposes. That's my point.
And okay, go ahead.
Okay, so as I understood, you can search in a whole cluster. You can also search in specific partition. Did I understood correctly?
Yes, exactly.
Okay.
How about the data loss prevention? Sorry.
Data loss?
Yeah, like do we need like taking the backups and snapshot as a traditional databases and recovery?
Okay. So the way you do backup, yes, you have to do this. So backup, as we know, you're doing backup. The way you take backups in a Cassandra cluster is via snapshots. So you're not copying all the data, which is SS tables, because SS tables are immutable. You can't change them once they are created. You can copy them aside like, right? So you're copying them aside and taking the snapshots, right? So when you have a failure, you can you're restoring those snapshots. But I'll tell you this it really depends also on the hardware that is there for your cluster. Depends on the on how mature they are, how reliable they are, because replication, because we're replicating our data already, that is some sort of a backup for us already, right? So sounds like if you have a copy of your data in 3 nodes and everyone is equal, so there's no master, this is not a big concern for backup procedures, I would say. And plus, if you have another data center out there geographically at a different distance, right?
So the content of mem table also, you can make a snapshotting the content of mem table, because there was a sesh table which is in the disk, but then mem table.
Can you please come back again? Can you?
Oh, sorry. Can you hear?
Yeah, yes, can hear now.
Because there was 2 types of tables, yeah? Mem table, which is in memory, and then SS table, which is on the disk. So let's say if you take the backup, and if then you'll lose a node, that the content of mem table is getting flushed out, or?
If you lose a node, well, that's something unavoidable, right? So it's, if you have a node, portion of the table in the mem table, and it hasn't yet been flushed to the SS table, right? So node gone, SS table can be restored, some sort of earlier version of this SS table, but mem table is gone, right? Because mem table is not like, mem table is not written to the SS table at every write, right? So it's not written to the SS table at every write. But what can save you in this case, I'll add this, what can save you in this case is your commit log, right? Commit log, which is the purpose of which is to store your data that was there in the mem table, but it was not there in the SS table at the time when crash occurred, right? So for example, so what I'm trying to say is this. Let's say your SS table is empty. You have written 1, 2, 3 to the mem table, right? 1, 2, 3. Even though this table hasn't been flushed to the disk yet, so no SS table is there for this table yet. 1, 2, 3 will be there in the commit log, right? So even though you lose the mem table, the commit log at recovery, commit log will restore and recover your data. So this procedure, I'm not sure if I was lost when I was speaking.
I think that there was a bit, but you're back.
Okay, so this procedure of recovering database is pretty standard, just like with any RDBMS. Okay. There's a transaction log, redo log, they call it differently, WAL log, so that's one of the same thing. Commit log serves the same purpose, to make these changes durable, right?
Okay. And the thing is, any other like managed services like cloud providers provided at this point, like for Cassandra?
DataStax Enterprise is one of them. I think even a few of them, maybe the only one on the market now that provides cloud-based Cassandra clusters, Cassandra machines. DataStax Enterprise. If you just Google, you'll find it.
Yeah.
They're emailing me constantly about this, by the way.
Yeah, I think I have a plan. Yeah, working over there. So how about, do they have like API support? Like if you, let's say if I install in Kubernetes cluster, and can I just?
Not sure about this. Not sure about this.
Not sure. Okay. Not sure if it was like any sharding, that anything relevant for the Cassandra. Because I think you mentioned about the partitioning, but how about the sharding, the data?
Actually, partitioning is that, so this partitioning term that we use this partition key actually defines the partition where a particular tuple will be in your cluster. So let me start from the beginning for this question. In a Cassandra table, every table requires a primary key, every table. So you can't create a table without a primary key, right? primary key itself contains of two parts. One of them is partition key. The other one is clustering key. So partition key, let's say ID name columns, for example, ID and name, two columns. This is my primary key. ID here, I can declare it ID as my partition key and name as clustering key. So the way Cassandra partitions your data, the way it decides on what node that tuple will reside is via is up to the partitioner. Partitioner takes this value of specific value of this ID, for example, 5, hashes it and says, hey, this 5 will reside on node number 2 and sends that to node number 2 and plus sends replicas as well. So this is how partitioning works there. And the other row comes along with value of 10. 10 gets partitioned and says, hey, this 10 will reside on node number 50. So this tuple will go to node number 50 and 2 more replicas, for example, to 60 and 70. So this is how data goes, becomes partitioned throughout the cluster. It's up to the partitioner to decide. Sharding is used, I think, this is the term, this is the one and the same thing, right? So sharding and partition. So sharding, sometimes used in NoSQL data stores. Partitioning term is used in RDBMS world. So they use partitioning, right? Sometimes sharding partition, so it depends on the vendor really. So Oracle, yeah. So they are. This is one and the same thing.
Okay, so it's more distributing and scaling the nodes, but also can it dynamically resize the cluster? That let's say if you remove the pieces and then will it come down, just saving and go up and down?
Yes, it does.
Or it's more mono. Okay.
It does so. So when you add a new node or you remove a node, Cassandra will do it for you. And so it is quite automatic, even though with large volumes you may have some problems, let's say, like because lots of data will be restreamed now, right? So it will be shuffled around. But when you add a node, Cassandra will detect that, hey, there's a new node, and now portion of the data from the other nodes should be streamed to that new node. And to minimize that streaming, Cassandra introduces the concept of vNodes, virtual nodes, where every physical node will be regarded as several virtual nodes. So there's a parameter that you can control this value, num tokens, I think, by default 128. So this is thanks to the consistent hashing, by the way. So yes, this is possible. I mean, and when you remove a node, so data will be restreamed from this removed node before it goes offline to the other nodes, then this node will be taken offline.
Okay, awesome. Because I worked quite a bit also like Kafka cluster. It reminds some terms there as well, like it's using Zookeeper. I don't know if you have the familiarity, that's kind of rebalancing and all these pieces the way it does.
Yeah, Zookeeper, Kafka, yes, I've heard about them. I read about them as well, and I think in the near future I will be involved in some interesting projects associated with Elasticsearch
Kafka?
and things like this.
Elasticsearch.
Yeah, things like this.
Awesome. I think it was a first intro for me also. I think we had during the school, but it was a while. I think it was a good refresher. Thanks so much for that. It was really informative.
Okay, thank you too, guys. Thank you.
Indicative. And not sure if any other folks, if you have any questions and last minute questions. And hopefully you enjoyed. If no questions, and don't be shy and reach out to Fadai. I think if you have the Fadai's details, maybe you can just click.
Yes. So thank you much for joining.
Okay, thank you too for your invitation. Yeah. Thank you for organizing all this, guys. I really enjoyed being here, and actually these questions that are hitting me. So this is the thing that I like most about talks of this sort, because this is the thing actually that reveals your knowledge and makes you think about something that you don't know, to research about something later. Okay, that's
I
great.
think that you are lucky, because I haven't really had much experience with Cassandra. Otherwise, I will have more questions, but definitely for the next one, I will do my homework.
Okay.
Yes,
So,
and
just-
we hope that we will have you as a guest lecturer in our next sessions for another topic as well, if you don't mind. Yeah, today's discussion was great. It was very informative. Thank you very much.
Okay, thank you
for
too, guys.
accepting.
Okay, see you later. Bye bye.
Thank you.
Thank you. Bye
Bye
bye.
bye. Thank you, Elvira. Bye bye.
Thank you. Thank you.